So far, we have not touched on optimization. So we looked at simulation of three strategies, and then we used risk sim table to try different what if kind of analysis. But now let's turn our attention to optimization, because we doing sim table is okay if there are only a few options, like handful of options, then you can set it up and you can run. But if you have thousands of options, well, even hundreds of options, would be cumbersome for us to set up and then run the simulations. It's probably easier, definitely easier to automate it, and that's what optimization does. The risk has risk optimizer, and that has some features that we can use um, to find the best possible or within reason best decision variable values. Okay, so sim table is cumbersome, large range of values. So with optimization, of course the optimization will work well if we guide the optimization in a judicious and efficient way. Otherwise, optimization can take forever to run, because especially in the simulation situation, each simulation can take uh, a bit of time, and adding up, if you have thousands of different possible values, and each has to be run like 10,000 repetitions, and you can see that the computational burden can quickly add up. So we have to be careful. We'll talk more about that in a little bit. So let's look at the basic contours. And if you have done linear programming in 5835, the quantitative methods class, then you already have a background in, or you have the basic concepts of optimization. So optimization basically has three components to it. One is decision variables. So those are the variables whose value that we want. We want to set values. It's in your control, but we want to know what the best values are for us to set up those variables. And then there are a bunch of constraints. There are two kinds of constraints. One is what the decision variables themselves can have. So some decision variables will have to be positive. Some decision variables will have to be greater than some other decision variable, and there are a whole range of possibilities there. And then there is another kind of constraint which is not directly like range like constraints on decision variables, but things that you calculate from the decision variables, and then the resulting values will have to be certain, certain minimum or certain maximum, and things like that. So that's the second set, constraints. And then the third component is the objective function. What are we trying to do? What is the criterion for selecting the values for decision variable? The decision variable values need to be selected in such a way that the constraints are not violated. But also we want something, how do you determine a bunch of values that do satisfy the constraints? Which set of values is preferable? And that's what objective function is. So if it is profit, then you want those values of the decision variables that will maximize the profit. If it is cost, you want those set of values that will minimize the cost, and so on and so forth. Now, how do we go about finding this optimal solution? And of course, one way is trial and error method. That's what we did with risk sim table. So we tried to come up with the best combination of values possible, or maybe the best value is in this range. So let's go ahead and try each and every value, and then pick the best. And of course, if you have only 10 variables, decision variables to select from, and that gives you 1024 possibilities. That's bad enough, but this is really a toy problem when you're talking about real business situations where the number of variables can very easily add up to 50 or more. And if you have 50 variables, and each variable can, further restricting assumption is that each variable, and even here we are talking about each variable having only two possible values, which is really not the case. Each variable can have any number of values, but even in the case of just two possible values, 10 to the 2 to the 10 gives you that many possibilities, and if you have 50 variables, then it's just impossible. So this is impractical trial and error. If you have only few little combinations of values that you want to try, 10, 15, okay, that's fine, but anything beyond that, sim table is useless. Now, optimization solver, okay, so we can use a solver to optimize, and in this case you can look at it in two different ways. Okay, one is the objective function is well behaved, so which means there is a clear shape, okay, there is a clear maximum. Okay, so here, even though it is not linear, then you still have a well-defined maximum. And in the case of if the curve is reversed, then you have a well-defined minimum. So if that is the case, then the decision or the solver can see, all right, now if I keep if this is the decision variable, let's assume for the sake of understanding there is only one decision variable. Now if I keep increasing the decision variable in this range, the objective function value keeps increasing. So you want to keep increasing the decision variable value. But if you're on this side, decreasing the decision variable value is what will give you an increase in the objective function. So you can try increasing in this range and decreasing in this range, and then you slowly march your way to the peak, right? Or the trough in the case of minimization. Okay, so this technique is called hill climbing technique. And of course, hill climbing technique will work if the objective function is well behaved. There are no disruptions and so on. But take a look at a case like this, where there is discontinuity. So if the decision variable is in this range, and if you use the hill climbing technique, then you'll find this to be the best value. Okay? And this is called local optimum. Again, if you start out in this range, you'll find that point and then stop, and you would have missed this. So this is the global optimum. So how do you if it is a well-behaved function, then there is only one optimum. There is no local local optimum is the global optimum, so no problem. But if there are discontinuities, okay, discontinuities are introduced in Excel, like if you have an if function or a max function or min function, those functions introduce discontinuity. Then it's possible that you ended up with a local optimum and you missed a global optimum. So what can we do in that kind of a situation? So goal is to find the true global optimum, okay, when you have discontinuity in objective function. There are two approaches that you can take. One is multi-start. Okay, so that means you don't start with one possible initial value for the solution and then done with it. No, you take several initial starting point. So hopefully it'll cover all the ranges. Okay, so you break down the possible values into smaller set of ranges, and you pick one starting value from each of those ranges and run through the optimization solver from each of those initial solutions. And hopefully that will get you the best possible global optimum. Okay, still there is no guarantee, but it's more likely than just starting out with one single initial value and not consider other initial values. Okay. Another approach is called evolutionary or genetic algorithms. So here you use random jumps in the decision variable. So you start a decision variable, and then instead of just simply increasing and decreasing, you jump randomly. So on that way you're going to cover more of the ranges here, and you're more likely to find the global optimum. So it prevents premature convergence to a local optimum. Okay. Now, both of these approaches are available in Excel Solver. So if you look at Excel Solver, okay, if you go to Data Solver, okay, and oh, it has some stuff there. It's okay. So if you go into options, all right. So if you go to GRG nonlinear, you see multi-start. So you can say if you click that, then it will use multiple starting point. Of course, that's going to take more time to solve a problem without it. And then you have the evolutionary uh, option. So you can use that. So both are available in Excel Solver, but there are some limitations. One thing, the Excel Solver is a deterministic model. It doesn't do simulation. And also there are some other problems. We won't get into that. There is a solver for that which is more advanced, which takes care of um, those issues. We will not go there because that's not part of the simulation modeling that we are talking about. The risk optimizer, uses both. It can do both deterministic and simulation. Yeah, and that's what we're going to do to our airline revenue model that we have been discussing.